Venus is hiding something, and for 30 years, NASA knew it. Not the kind of knowing where scientists have a hunch and write a paper about it, the kind of knowing where committees are formed, budgets are debated, missions are designed and then quietly shelved, where engineers spend careers building technology for a planet they are never actually sent to. For 3 decades, the most scientifically compelling destination in the inner solar system was systematically avoided when it came to one specific type of mission. Not orbiters, not atmospheric probes, not landers that last a few hours before getting crushed and cooked. Those missions happened, but one particular mission, the one that would have told us more about Venus than anything else ever could, was left on the table again and again and again. A direct sample return from Venus. Bring back a piece of the planet. Scoop up rock and soil from the Venusian surface, seal it in a container, launch it off the planet, and carry it back to Earth where scientists can study it in laboratories with instruments far more sophisticated than anything we could ever land on another world. That mission, the one that would have rewritten our understanding of planetary science, kept getting proposed and kept getting declined. If you want to understand why that matters, you first have to understand what Venus actually is. Because most people, if they think about Venus at all, think of it as Earth's twin, the planet next door. A little hotter, sure. A little cloudy, but fundamentally similar. A rocky world roughly the same size as ours, sitting in the same neighborhood of the solar system, made of the same basic ingredients. That description is not wrong, but it is dangerously incomplete. And the gap between what we know about Venus and what we think we know about Venus is exactly where this story lives. So if this is the kind of deep dive you want to go on, make sure you subscribe right now, because we are just getting started, and this one goes places most space documentaries never bother to go. Let's begin at the beginning. Venus is the second planet from the Sun. It orbits at an average distance of about 108 million kilometers, compared to Earth's 150 million. In terms of size, it is strikingly close to our own world. Venus has a diameter of about 12,104 kilometers. Earth's diameter is 12,742 kilometers. These two planets are so similar in size that for a long time they were considered near identical in terms of their basic structure and composition. Same rocky surface, similar internal layering, roughly comparable gravity. If you stood on Venus, you would feel about 90% of the gravitational pull you feel standing on Earth right now. On paper, Venus looks like Earth's almost perfect sibling, but then you look at the details, and the details are where everything goes wrong. The atmosphere of Venus is made almost entirely of carbon dioxide, not the small percentages you find on Earth or Mars. We are talking about 96.5% pure carbon dioxide, with the remaining few percent being mostly nitrogen and trace amounts of sulfur dioxide and other compounds. This thick blanket of CO2 wraps around the planet like an insulating shell, trapping heat from the sun in a runaway greenhouse effect so extreme that the surface temperature of Venus sits at around 465 degrees Celsius on average. Not 65, not 165 degrees. That is hot enough to melt lead, hot enough to melt tin, hot enough to melt zinc. The surface of Venus is, in terms of temperature, one of the most hostile environments in the entire solar system, hotter even than some regions of Mercury, the planet that is actually closest to the Sun. And the pressure. The atmospheric pressure on the surface of Venus is about 92 times greater than what you experience at sea level on Earth. Standing on the surface of Venus would be roughly equivalent to diving nearly a kilometer beneath the surface of Earth's ocean. Every square centimeter of your body would be crushed by a weight it was never designed to withstand. Then there is the cloud layer. Venus is permanently shrouded in thick clouds that make it impossible to see the surface from orbit using ordinary visible light. Those clouds are not made of water vapor the way Earth's clouds are. They are made of sulfuric acid droplets, concentrated sulfuric acid, hanging in layers between roughly 45 and 70 kilometers above the surface, reflecting about 70% of the sunlight that hits the planet, and giving Venus that brilliant white glow you can see in the night sky. So that is Venus, a world the same size as Earth, wrapped in acid clouds, crushed under 90 times atmospheric pressure, baking at temperatures that melt metals, with a surface you cannot even see from space. Earth's twin, in the loosest possible sense of the word. And here is the thing that makes this all so scientifically urgent. We do not know why. We do not know why Venus turned out this way. We do not know at what point in its history the runaway greenhouse effect kicked in. We do not know whether Venus ever had liquid water on its surface, which some models suggest it might have, for potentially billions of years during the early solar system. We do not know what the Venusian crust is made of at the chemical level in any meaningful detail. We do not know whether Venus ever had plate tectonics. We do not know whether it had or still has in some form volcanic activity. We do not know whether the hellish environment we see today was always the case, or whether Venus was once far more like Earth, and something catastrophic changed it. These are not minor gaps in our knowledge. These are fundamental questions about how rocky planets form, how they evolve, and what determines whether a planet ends up as a cradle for life or a pressure cooker that makes lead puddles. These questions have direct implications for understanding Earth's future. They have implications for how we evaluate every rocky planet we find orbiting other stars. They are among the most important questions in planetary science, and a sample return mission would answer them, or at least, it would answer them better and more completely than any other type of mission we could send. Because when you bring back a physical piece of another world, you can study it with instruments that haven't been invented yet. You can subject it to tests that would take years to design. You can look at its isotopic ratios, its mineralogy, its chemical structure, its age. You can do things that no rover or lander, no matter how sophisticated, can ever do. We know this because we did it with the moon. The Apollo samples, those bags and crates of lunar rocks brought back between 1969 and 1972, are still being studied today. New papers are still being published based on lunar samples that were collected more than 50 years ago. Because analytical chemistry keeps getting better, and every time it does, those rocks tell us something new. We did it with Mars, not through a crude mission, but through sheer cosmic luck. There are meteorites sitting in our museums and research labs right now that originally came from Mars, ejected by ancient asteroid impacts, that drifted through space for millions of years before falling to Earth. Scientists have extracted extraordinary information from those rocks. Information about the Martian water cycle, about the planet's volcanic history, about its ancient magnetic field, all from rocks that arrived here naturally. Imagine what we could learn if we deliberately collected samples from Mars, selected exactly the right spots, the most geologically interesting locations, and brought them back in controlled conditions. That is exactly what NASA's Mars Sample Return Program is designed to do, and it is considered one of the crown jewels of planetary science for that reason. So why not Venus? Why, for 30 years, did every serious proposal for a Venus sample return mission get quietly set aside? The answers to that question are more interesting than you might expect, and some of them only recently became fully public through declassified documents, official mission reviews, and a slow trickle of candid statements from scientists and engineers who spent those decades on the inside of these discussions. There are three primary reasons, three fundamental obstacles that, taken together, made a Venus sample return mission not just difficult, but seemingly impossible for a very long time. Let us go through them one by one, because each one is a story unto itself. The first reason is the surface environment. We already established that Venus is hot, 465 degrees Celsius hot. But when you are designing a spacecraft, that number stops being an abstract fact and becomes a very specific engineering nightmare. Every piece of electronics ever built for space exploration operates within a thermal range. Silicon-based computer chips, the kind that run every spacecraft we have ever launched, stop functioning reliably at around 125 degrees Celsius under normal conditions. Radiation-hardened versions, the specially built chips designed for the hostile radiation environment of space, can push that tolerance up to maybe 200 degrees in some cases. A handful of experimental designs have been tested at temperatures approaching 300 degrees. Venus surface temperature, 465 degrees Celsius. That is not a gap you close with better insulation or a clever heat shield. You could pack a lander in the most sophisticated thermal protection system ever designed, and give it maybe a few hours before the heat wins. Which is exactly what happened with the Soviet Venera probes, the most successful surface missions ever sent to Venus. The Soviets sent a series of Venera landers to Venus between the 1970s and 1985. These were extraordinary machines, purpose-built to survive the Venusian surface long enough to take measurements and send back data. Venera 9 and 10 sent back the first photographs of the Venusian surface in 1975. Venera 13 and 14 in 1982 survived long enough to take color photographs and conduct limited soil analysis. The longest any of these probes survived on the surface was 127 minutes. That was Venera 13, 2 hours and 7 minutes. Then the heat and pressure overwhelmed the spacecraft and it went silent forever. Now think about what a sample return mission requires. You cannot just land, scoop up some dirt in 2 hours, and then launch yourself back into space. The landing phase alone, descending through that thick atmosphere, takes time. Then you need to actually collect the samples, which means drilling or scooping at the surface, sealing the material in a container, and verifying that the collection was successful. Then you need to launch a sample return vehicle from the surface of Venus, which requires a rocket motor firing in an environment that is actively trying to destroy every component of your spacecraft. Then you need to achieve orbit around Venus, rendezvous with an orbiting carrier spacecraft, transfer the sample container, and then begin the long journey back to Earth. Each one of those steps is enormously complex. Doing any one of them in a 465-degree, 92-atmosphere environment is an engineering challenge that dwarfs almost anything else in the history of spaceflight. Doing all of them in sequence, with a spacecraft that must remain functional from beginning to end, is something that as of today, we do not yet have the technology to accomplish. This is not speculation. This is the conclusion that engineering review after engineering review came back with every time a Venus sample return proposal was examined in detail. The thermal and pressure environment of the Venusian surface is so extreme that no existing propulsion system, no existing electronics platform, no existing material science could support a mission architecture that required sustained operation on that surface. The Soviets actually explored one potential solution back in the 1980s. They considered building landers that were cooled internally, essentially a spacecraft with a refrigeration system built into it that would keep the electronics cold even as the outside cooked. The problem is that a refrigeration system requires power. Running a refrigerator hot enough to keep your internals at operational temperature inside a 465-degree oven would require enormous amounts of energy. Energy that the spacecraft would need to be carrying in battery form, since solar panels cannot generate enough power in the thick Venusian atmosphere. And batteries are heavy. The heavier your lander, the more fuel you need to land it, and the more fuel you need to launch your sample return vehicle from the surface. The mass budget for such a mission spirals upward very quickly until you end up with a spacecraft that is simply too large and too heavy to launch with any rocket that exists. NASA's internal reviews of Venus sample return proposals in the 1990s and into the 2000s repeatedly ran into this same wall. The engineering was not impossible in a theoretical sense, but it was impossible in a practical sense given the budgets, the technology readiness levels, and the available launch vehicles of the time. Every mission concept that got developed to any level of detail came back with a price tag and a technical risk profile that made it impossible to justify when you could instead send a Mars mission that would actually work. And so Venus sample return kept getting pushed to the back of the line, not because no one wanted to do it, but because the environment itself made it impossibly hard. The second reason is contamination, and this one is more subtle, but in some ways even more significant. When you think about contamination in a space context, most people immediately think about planetary protection. The idea that we might accidentally transport Earth microbes to another world and contaminate it before we have a chance to study it properly. That is a real concern, and it drives a lot of the sterilization protocols that NASA applies to Mars missions in particular. You do not want to send a lander to Mars looking for signs of ancient life and then discover that the only microbes you find are the ones that hitched a ride on your spacecraft from a clean room in California. But the contamination problem for Venus sample return runs in the other direction, and it is arguably more complicated. Here is the issue. Venus's atmosphere, while largely composed of carbon dioxide and sulfuric acid, contains trace amounts of other chemical compounds that are not fully characterized. We know they are there. We have detected them from orbit and from atmospheric probes. But we do not know exactly what they are in every case, or how they might interact with Earth's atmosphere and biosphere if they were brought back in an uncontrolled manner. Now, let us be clear about something important. The scientific consensus has long held that Venus does not currently host life on its surface. The temperature and pressure make that essentially impossible for any life as we know it. The surface is geologically active in ways that would sterilize any surface biology. The conditions are simply too extreme. But the atmosphere is a different conversation, and it became a dramatically more public conversation in September 2020, when a team of researchers announced the detection of phosphine in the upper Venusian atmosphere. Phosphine is a molecule made of one phosphorus atom bonded to 3 hydrogen atoms. On Earth, it is produced in 2 primary ways, either through industrial chemical processes or through biological activity, specifically by anaerobic microbes, bacteria that live in environments without oxygen. When the researchers announced that they had detected phosphine in Venus's clouds at concentrations that could not be explained by known chemistry, the implications were extraordinary. If confirmed, it would mean that something in the Venusian atmosphere was producing a molecule that, on Earth, is primarily a biosignature, a chemical marker of life. The announcement was immediately controversial. Other scientists challenged the data, the analysis, the calibration of the instruments used. The debate has not been fully resolved. Subsequent analyses have suggested that the phosphine signal may have been much weaker than initially reported, or may have been an artifact of the data processing. The original team has stood by their work while acknowledging the uncertainties. As of today, the question of phosphine in Venus's atmosphere remains an open scientific debate. But here is what that announcement did to the Venus sample return conversation. It turbocharged the contamination concern. Because if there is even a theoretical possibility, however small, that Venus harbors some form of microbial life in its cloud layers, then bringing back Venusian material without absolute certainty that it poses no biological risk to Earth becomes an enormous and potentially politically unacceptable proposition. We have protocols for this. NASA's planetary protection policies are governed by an office specifically dedicated to evaluating and managing the risk of cross-contamination between Earth and other worlds. Any sample return mission from a world that cannot be definitively ruled out as a potential host for life, what the protocols call a restricted Earth return, must meet an extraordinarily high bar for containment. The samples must be kept in conditions that guarantee no Venusian material could escape into Earth's environment, from the moment of collection all the way through to final storage, in a facility with the highest possible biosafety standards. For Mars sample return, this has already been a significant planning challenge. The proposed Mars sample return curation facility is being designed with containment systems that exceed those of the world's highest-level biological research labs, the BSL-4 facilities where scientists work with the most dangerous pathogens known. And Mars is considered a potentially restricted return case, largely based on the historical possibility that it once had liquid water and may once have hosted microbial life. Venus, post-phosphine announcement, now occupies an ambiguous but deeply complicated space in that framework. The surface material, rocks and soil collected from a 465-degree environment, is almost certainly sterile. But the mission architecture for a Venus sample return cannot ignore the atmosphere. Getting a sample off the surface and back to Earth means passing through that atmosphere. A launch vehicle exiting Venus would have to punch through those cloud layers where, theoretically, any atmospheric biology would be concentrated. Can you design a containment system for a sample canister that is absolutely guaranteed to prevent any atmospheric material from contaminating the interior of the container during ascent? Can you build a sealing mechanism that functions flawlessly in 465-degree heat, at 92 atmospheres of pressure, and maintains its integrity through the violent dynamics of a rocket launch? Can you certify, with the level of confidence that planetary protection protocols demand, that no atmospheric Venusian material has been incorporated into the sample? The engineering reviews that examined these questions concluded that you probably cannot. Not yet. Not with current technology and current materials. And in the absence of that certainty, the path toward a restricted Earth return certification for a Venus sample becomes extraordinarily long and expensive. This is the second reason Venus sample return kept getting avoided. Not because scientists were not interested, but because the contamination risk framework, combined with the post-phosphine atmospheric biology question, made the regulatory and engineering hurdles for certifying a safe sample return essentially prohibitive given the technology of the past 3 decades. The third reason is arguably the most interesting one. Because it is not about the planet at all, it is about us. The third reason is strategic science prioritization, and the way that Mars came to dominate NASA's planetary exploration agenda in a manner that effectively crowded Venus out of the most ambitious mission categories for an entire generation. To understand this, you have to go back to the early 1990s and the way NASA structures its planetary science program. The agency does not simply decide on its own what missions to fly. The priorities of NASA's science program are shaped in large part by a process called the Planetary Science Decadal Survey. This is a document produced roughly every 10 years by the National Academies of Sciences, Engineering, and Medicine through a process that involves hundreds of scientists submitting white papers, debating priorities, and ultimately agreeing on a ranked list of recommended missions for the coming decade. The Decadal Survey is enormously influential. When NASA's budget is being divided up, these priorities carry serious weight. Missions that are ranked highly in the Decadal Survey get funded. Missions that are ranked lower or not included get pushed back or canceled. In the 1991 Decadal Survey, the emphasis for inner solar system exploration began shifting heavily toward Mars. There were several reasons for this. The discovery of what appeared to be possible evidence for ancient microbial life in the Martian meteorite ALH 84001, announced in 1996, electrified public interest in Mars and drove enormous political support for Mars missions. The success of Mars Pathfinder in 1997, which put a small rover named Sojourner on the surface and captivated the world with its results, demonstrated that Mars missions could work, that they could succeed, that the public loved them, and that they generated the kind of media coverage and congressional enthusiasm that made funding easier to secure. Mars became the focal point, not just scientifically, but culturally. The idea of Mars as a destination for future human exploration took root in the public imagination. The astrobiology angle, the search for life, was a powerful narrative that drove sustained interest in the red planet in a way that was easy for policymakers to understand and support. Venus did not have that story. Venus had no life angle, or at least not one that anyone was comfortable using as a funding argument, because claiming there might be life in Venus's clouds was speculative in a way that was difficult to defend in a budget hearing. Venus had no accessible surface, no rover-friendly terrain, no possibility of human exploration in any near-term time frame. Venus was scientifically fascinating, but it was a hard story to tell to a congressional committee that wanted to know why they should spend billions of dollars on a mission that would last 2 hours before being crushed. So in survey after survey, Mars sample return ranked higher. Mars was the priority. Mars got the flagship class mission budget allocation. Venus got smaller missions, orbiters, atmospheric probes, important science undoubtedly, but not the crown jewel of a sample return. The 2003 Decadal Survey recommended Mars sample return as the top priority for large missions. The 2011 Decadal Survey, commonly called the Vision and Voyages Survey, again placed Mars sample return at the top of the large mission category. Venus, in both cases, received recommendations for smaller Discovery or New Frontiers class missions. This is not a conspiracy. It is not a cover-up. It is the outcome of a rational prioritization process in a world where budgets are limited and you cannot do everything at once. But the practical effect was that for 30 years, Venus sample return was never in the running for the funding level that such a mission would require. Every time the idea was raised seriously, the response from the prioritization framework was, essentially, Mars first. The declassified and publicly released internal reviews from this period tell a consistent story. Program scientists who advocated for Venus sample return found themselves in a catch-22. The mission was technically too hard to propose without significant technology development funding. But the technology development funding was not available because the mission was not a high enough priority to justify it. And the mission could not become a high enough priority until someone demonstrated that the technology to accomplish it actually existed. Round and round the loop went, for 3 decades. But here is where the story changes, and why we are talking about this now. Something shifted in the 2020s. Something significant enough that Venus sample return has moved from a theoretical aspiration to an active planning conversation in a way it never quite managed to before. Part of it is the phosphine announcement. As controversial as that finding remains, it fundamentally changed the way people think about Venus from a science strategy perspective. If you cannot rule out biology in the Venusian cloud layer, and you are serious about the search for life as a core mission of planetary science, then you cannot just keep sending small missions to Venus and hope that orbiters will eventually answer the question. You need samples. You need to characterize the atmosphere at a chemical and potentially biological level in ways that only returned samples can provide. Part of it is the technology development work that has quietly been progressing for years. The High Operating Temperature Technology Program, sometimes referred to as HOT Tech, was a NASA initiative specifically directed at developing electronics and systems that can operate in the extreme environment of Venus's surface. The program funded research into silicon carbide semiconductors, materials that can function at temperatures far higher than conventional silicon chips. Early results showed that silicon carbide-based circuitry could operate at around 500 degrees Celsius for extended periods of time. That does not solve every problem, but it is a significant step toward the kind of electronics that a long-duration Venus surface mission would require. There was also work done on high-temperature mechanical systems, actuators and drilling mechanisms and sealing technologies that could potentially function at Venus surface conditions long enough to collect and seal a sample. None of this was ready for a mission in the 2010s, but the trajectory of the research suggested that within a decade or two, the technology readiness level for these critical components could reach the point where a serious mission architecture becomes feasible. Part of it is the 2023-2032 Planetary Science Decadal Survey, released in 2022 under the title Origins, Worlds, and Life. This survey did something that previous surveys had not done in the same explicit way. It elevated Venus to a top priority. The survey recommended a flagship-class mission to Venus, the Venus flagship mission concept, as one of the highest priorities for large strategic missions in the coming decade. It also recommended the Enceladus Orbilander mission at the top of the large mission priority list, but the elevation of Venus to flagship status was a genuine shift in the strategic landscape. Simultaneously, NASA announced in 2021 that it had selected 2 Venus missions from its Discovery program: Da Vinci, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, and Veritas, the Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy mission. Da Vinci is designed to drop an atmospheric probe through Venus's atmosphere, characterizing it in extraordinary detail as it descends. Veritas would map the Venusian surface with high-resolution radar, providing global geological context. These are not sample return missions, but they represent a fundamental investment in the infrastructure of Venus knowledge that would make a sample return mission more achievable. Because one of the problems with designing a Venus sample return is that we do not know enough about the surface geology to know where to collect samples from. You need detailed surface mapping. You need atmospheric chemistry data. You need to understand the thermal environment at specific landing sites. Da Vinci and Veritas would begin to provide that foundation. And then there is the European Space Agency. ESA selected its own Venus mission, called Envision, which will provide complementary surface and atmospheric observations. The combination of these 3 missions, Da Vinci, Veritas, and Envision, represents the most comprehensive push to study Venus that has ever been organized, and it is explicitly intended, in the scientific community's planning documents, as a precursor to a sample return. So the 30-year avoidance is ending, not yet with a sample return mission, but with the systematic laying of groundwork that makes one conceivable in a way it never quite was before. But let us go back to the science for a moment, because the reason any of this matters, the reason sample return from Venus is worth spending this much time discussing, is the question it would answer. And that question is one of the most profound in planetary science. Why is Venus the way it is? On its face, that seems like a narrow question about one specific planet, but it is actually a question about the divergence of worlds, about the pathway from formation to habitability, about the conditions under which a rocky planet can support liquid water, a stable climate, and eventually life, as opposed to the conditions under which a planet tips over into runaway greenhouse heating and becomes an uninhabitable furnace. Here is what we know, or think we know. Venus and Earth formed at roughly the same time, about 4.5 billion years ago, from the same cloud of material in the early solar system. They are nearly identical in size and composition, or at least in the broad strokes of their composition. Early in their histories, both planets were almost certainly covered in magma oceans as the intense heat of planetary formation slowly radiated away. Both planets probably had significant amounts of water, either from the raw materials they formed from or delivered later by impacting comets and asteroids. At some point, the paths diverged. Earth ended up with liquid oceans, a nitrogen-oxygen atmosphere, plate tectonics, and life. Venus ended up with a surface hot enough to melt lead, a thick CO2 atmosphere, no liquid water, and no detectable life. What happened? When did it happen? And could it happen to Earth? There are several leading hypotheses. One is that Venus received slightly more solar radiation than Earth due to its closer orbit, and this small difference was enough to prevent water from condensing on the surface. Without surface oceans, the water in Venus's early atmosphere could not be absorbed and locked into rocks the way it was on Earth. Instead, it stayed in the atmosphere, where ultraviolet radiation from the sun broke the water molecules apart, allowing the hydrogen to escape into space and the oxygen to react with surface materials. Without water, the planet's carbon dioxide could not be pulled out of the atmosphere through the same weathering processes that regulate Earth's carbon cycle. CO2 built up, temperatures rose, and the spiral of the greenhouse effect accelerated until it reached the hellish conditions we see today. This is sometimes called the moist greenhouse scenario, and it suggests that Venus's fate was set early, possibly within the first 100 million years of its history. But there is another hypothesis, more unsettling in some ways. Maybe Venus was habitable for much longer than the first hypothesis suggests. Some climate models have shown that with a slower rotation rate, which Venus does have, spinning once every 243 Earth days, and with the right initial cloud cover patterns, Venus might have been able to maintain habitable surface temperatures for up to 3 billion years after its formation. 3 billion years is a very long time. Long enough on Earth for simple single-celled life to evolve and begin transforming the planet's chemistry. If Venus was habitable for billions of years, and then something tipped it over into the runaway greenhouse state relatively recently in geological terms, that has extraordinary implications. It means that planets can be habitable and then lose habitability on timescales that are relevant to the history of complex life. It means that Earth's stability is not guaranteed, and it means that in the universe at large, there could be many worlds that once hosted life and no longer do, far more than models that assume early divergence scenarios would suggest. How do you test these hypotheses? How do you figure out which story of Venus is correct? The most powerful tool available is the rocks. Not atmospheric measurements, not orbital radar mapping, not spectroscopy from a distance. Actual physical samples of the Venusian surface, collected from geologically meaningful locations, brought back to Earth and subjected to the full battery of radiometric dating, isotopic analysis, and mineralogical examination that modern geochemistry can apply. Because the rocks on Venus's surface are not just rocks. They are a geological record. They contain minerals that formed under specific temperature and pressure conditions. They contain isotopic signatures that record the history of the planet's water. They can be dated precisely, telling us how old specific surface features are and whether the planet's geological activity has been continuous or episodic. They contain evidence of past volcanic eruptions, past tectonic activity, past interactions between the solid planet and the overlying atmosphere. And in the crust of Venus, If Venus ever had surface water, there would be hydrated minerals, phyllosilicates, carbonates, sulfates, the kinds of compounds that form when liquid water reacts with rock over long periods of time. Finding those minerals in Venus samples, or not finding them, would be a definitive test of the long habitability hypothesis in a way that no remote sensing can match. This is what sample return offers, not just data, not just measurements. The actual physical record of planetary history, preserved in rock and mineral and chemistry, waiting to be read. And we have been 30 years away from being able to read it. Let us talk about what the mission might actually look like, because this is not purely theoretical anymore. There have been detailed mission concepts developed, particularly in the last decade, and they are genuinely audacious pieces of engineering imagination. One of the most developed Venus sample return concepts, worked on by teams at NASA's Jet Propulsion Laboratory and at other institutions, involves a multi-stage mission architecture. The first stage is a massive lander, much larger and more capable than the Venera probes. This lander would be designed not just to survive on the Venusian surface for a couple of hours, but to operate there long enough to drill into the surface, collect multiple rock cores from different depths, and seal them into a return capsule. The drilling operation alone is a feat of engineering imagination. You need a drill bit that can cut through hard volcanic rock at temperatures approaching 500 degrees Celsius. You need mechanical actuators that can operate under those conditions. You need a sealing mechanism for the sample container that activates after collection and maintains an airtight seal throughout the remainder of the mission, including the violent dynamics of launch from the surface. The return vehicle is the second enormous challenge. Launching a rocket from the surface of Venus is not like launching from Earth or from Mars. On Mars, the thin atmosphere provides minimal aerodynamic resistance, and the lower gravity means you need less fuel to reach orbital velocity. On Venus, the dense atmosphere creates enormous drag for a vehicle trying to ascend, and while the surface gravity is similar to Earth's, the sheer density of the atmospheric column you need to push through makes ascent far more demanding than any comparable mission. The fuel for a Venus surface ascent vehicle also has to survive the surface environment. Conventional hypergolic propellants, the kind used in many spacecraft engines because they ignite spontaneously on contact, have operational temperature limits that fall well short of Venus surface conditions. Solid rocket motors might be more suitable, since they do not require the fuel and oxidizer to flow through pumps and valves that could fail at high temperatures. But solid rockets are less controllable than liquid engines, which creates challenges for the precision needed in a sample return architecture. One proposed solution involves keeping the ascent vehicle insulated and thermally protected from the Venusian environment for the duration of surface operations, essentially a spacecraft within a spacecraft, where the outer lander endures the heat and pressure, while the ascent vehicle inside is maintained at operational temperatures by the same kind of active cooling system the Soviets once considered. The energy budget for this approach is enormous, but some mission concepts have shown that it is achievable with advanced radioisotope power systems of the kind already used on missions like Cassini and New Horizons. Once the ascent vehicle has fought its way through the atmosphere and reached Venusian orbit, it needs to rendezvous with an orbiting carrier spacecraft that has been waiting, potentially for years. The orbital rendezvous is complex, but achievable with existing technology. The transfer of the sample container between the ascent vehicle and the carrier is a critical operation that has analogs in the Mars sample return architecture currently being developed. Then the carrier spacecraft begins its journey back to Earth, which takes months, followed by an atmospheric entry that must be designed to keep the sample sealed and intact through the fiery re-entry conditions. Each of these steps is solvable. Some of them are already solved in the sense that the technology exists in a form that could be adapted. Others require specific development work that has not yet been done, but is well within the range of what human engineering can achieve given sufficient funding and time. The critical technology gaps are primarily in two areas: high-temperature electronics and mechanisms for the surface phase of the mission, which the HET Tech program has been working to address, and the ascent vehicle propulsion system, which requires either a novel approach to solid rocket performance in the dense Venusian atmosphere or a significant advance in high-temperature liquid propulsion systems. NASA's internal cost estimates for a Venus sample return mission at the flagship level have ranged widely depending on the architecture assumed, but figures in the range of $4 to $6 billion over the full mission lifecycle are not unreasonable based on comparable missions. That is more expensive than most planetary missions, but comparable to other flagship projects like Cassini, which cost about $3.5 billion over its lifetime, or the Europa Clipper, which is currently estimated at around $5 billion. It is not cheap, but it is not impossibly expensive either, particularly if Venus continues to rise in the priority rankings in future decadal surveys. Now, there is another dimension to this story that is worth exploring, because the question of why Venus turned out the way it did is not just a scientific question about our solar system. It is a question with direct relevance to the search for life around other stars. We are living in a golden age of exoplanet science. The Kepler Space Telescope cataloged thousands of planets orbiting other stars. The TESS mission continues that survey. The James Webb Space Telescope is beginning to characterize the atmospheres of rocky exoplanets in ways that were impossible just a few years ago. And in the coming decade, missions like the Habitable Worlds Observatory, proposed in the most recent decadal survey, will push that capability further still. When we talk about potentially habitable exoplanets, we typically focus on the concept of the habitable zone, the range of orbital distances from a star at which liquid water could exist on a planet's surface. Earth is in the habitable zone of the Sun, Mars is at the outer edge of it, and Venus is at the inner edge, or perhaps just inside it depending on how you define the boundaries. The fact that Venus, which orbits within or very close to the habitable zone of the Sun, is spectacularly uninhabitable by any life as we know it, tells us something important. It tells us that being in the habitable zone is a necessary condition for surface habitability, but it is not a sufficient one. There are other factors we do not yet fully understand, that determine whether a planet in the habitable zone ends up like Earth or like Venus. This is what planetary scientists call the Venus zone, the inner portion of the habitable zone where planets are at risk of the same kind of runaway greenhouse fate as Venus. Current estimates suggest that roughly a third of rocky planets in habitable zone orbits might actually be in the Venus zone, at high risk of uninhabitable Venus-like conditions, despite being at the right distance from their star. If we could understand exactly what tipped Venus over, what the key differences were between Venus's formation and early history, and Earth's formation and early history, we would have a much better basis for evaluating which exoplanets in habitable zones are actually likely to be hospitable and which are likely to be dead ends. That knowledge would transform our ability to prioritize targets in the search for life. It would change how we interpret atmospheric spectra from exoplanets. It would refine our models of planetary habitability in ways that have ramifications for every future mission in the astrobiology program. Venus sample return is not just about Venus. It is about understanding rocky planet habitability across the universe. There is one more thread worth pulling here, and it concerns what we might find that we are not expecting to find. Science has a long history of its most important discoveries being things nobody predicted. The discovery that the Martian meteorite ALH 84001 contained what looked like possible microfossils, even if that interpretation remains contested, was not something anyone was specifically looking for when they picked up that rock in Antarctica. The discovery of water ice in permanently shadowed craters on the Moon was not obvious from orbital observations. The detection of organic molecules in the plumes of Enceladus by the Cassini spacecraft opened up an entirely new chapter in astrobiology that nobody had fully anticipated when Cassini was designed. Venus samples could contain surprises. They almost certainly would, because every time we have brought back physical material from another world or studied extraterrestrial material in the lab, it has told us things that our remote observations had not revealed. What minerals are on the Venusian surface that we do not know about? What does the isotopic record in the rocks say about the planet's early history? Is there evidence of ancient hydrothermal systems, ancient ocean sediments, ancient biological chemistry? We genuinely do not know. and the only way to find out is to go and get a piece of the planet and bring it home. The 30-year avoidance of that mission was not irrational. The three reasons, the impossible surface environment, the contamination risk framework, and the strategic crowding out by Mars, were each real and significant. Any one of them would have been a serious obstacle. Together, they were effectively insurmountable given the technology and priorities of the 1990s and 2000s. But things change, technology improves, priorities shift, and sometimes a detection in the clouds of another world, whether confirmed or not, is enough to crack open